So how are y'all doing? Alrighty. So if you haven't heard, we are the Science Brothers. My name is Gavin Science. I'm an electrical engineer that works at the Navy base in Panama City Beach. And this is my brother Dan Science.
I'm actually a physicist. Oh, hang on.
You gotta turn your mic.
Turn my microphone on.
Yeah.
I'm actually a physicist. Don't know what the microphone does. No, I work at the Navy base also as a physicist, but I like to do chemistry is my favorite science. So that's the sort of the stuff I brought here to show you today. So yeah, we're the Science Brothers. We are here to show you some cool science stuff to hopefully get you interested in science as a career and to learn about it in school.
But obviously, you're gonna totally be more interested in electricity because electricity is so much cooler than chemistry. Just thought I'd let you know.
Yeah. See, there's some people that agree. What? No, chemistry is the way to go.
Well, I shall have to.
I
shall have to entice you and show you the right way.
All right.
So, first thing I want to talk about, to start my expose, if you will,
Yeah, all right.
is I want to talk about static electricity. So, probably a dumb question, but who knows what happens if you have a balloon and you rub it in your hair? What happens to your hair? Just say it. Go for it. It wants to stand out, right?
Yeah.
Well,
okay.
What we have here is called a Van der Graaf generator. It does pretty much the same thing as the balloon in your hair. And it does not want to work for me today. My word. Well,
Electricity.
Electricity, okay. What I have is a smaller Van der Graaf generator. I can show you essentially the same idea. But what it does is both of these create static electricity, just like the balloon in your hair and other options. And I'm going to show you one way static electricity works. Dan, if he wants to touch that, he would show you what another option of static electricity is. It's one that might be more, it'll feel fine. It'll make your beard stand up, just like your hair.
Let me see this thing first. Oh.
But notice what we're doing here. So what this is it's called mylar. It's really thin tinfoil, and by itself, it's kind of limp, right? But as soon as I touch it on my Van der Graaf generator, it wants to go away from the Van der Graaf generator. Now, if it were to go back and forth like my larger Van der Graaf would, you would see that it would want to bounce back and forth between my hand and that dome. The reason we like to explain it is it's using concept of magnets. Who here knows about magnets?
Yeah. Yes. I've seen magnets.
They all
all
know
over the
about it.
place.
Good. So if you got a North Pole and a North Pole, what do we want to do? It's going to repel, that's right. If you've got a North Pole and a South Pole, what do they want to do? They want to attract, that's right. So what you saw with my smaller Van der Graaf generator is the mylar was the South Pole. And the Van der Graaf generator was a North Pole. And once it hadn't touched it, it was still in my hand, it wanted to go towards the Van der Graaf generator. Mm-hmm. But as soon as it touched it, you saw it got a little shock. And it got kind of springy, I guess. And then it didn't want to touch the Van der Graaf generator. Did you see that? I was kind of chasing it around. And that's because they were both North Poles at that point. Now,
Okay.
come on, Dan. You want to see?
Well,
you want to see what happens with static
No. I've heard that if you put your hand on these things, right, it makes your hair stand up. Maybe I can get my beard to stand up if I do it. Jeez.
Yeah. Oh, yeah, I forgot. Who knows what happens if you rub your socks on carpet, touch somebody? What happens?
Ow. So
Yeah, that's the other part of static electricity I forgot to tell you about.
Jeez.
So, now one thing I have to point out is what does this kind of look like, Dion? It's like a wand, right?
Oh yeah.
But it's not a magic wand. So this isn't magic. We're not doing no voodoo mess up here. This is science. And the reason it's science is because we can explain it.
Yeah. Okay.
Magic, you kind of can't explain, but science we can.
Right.
So as long as we're doing science up here, we're on the hook to explain it to you guys.
Yep. Okay. Well, that was pretty cool, except for the shocking part. That was dumb. But I've got other things here that I think is even cooler that you'll probably enjoy. Yeah. I got a whole fan club over here.
They got faith in you. I don't know why. What is this mess?
All right.
Oh, goodness.
Well, let's start with this one. This is a flask that's got some chemicals in it. So what color would you guys say this is? Used orange. What do you think, Gavin?
I'd give you a yellowish gold,
Yellowish.
closer to orange. Yeah, I'd give you
Gold,
that.
orange, something like that. Okay.
Big deal.
Well, now all I'm going to do is swirl it around a bit. And now what do we got?
Whoa.
Yeah.
Did you just switch flasks on me? I wasn't paying attention, but that's a completely different color.
Yeah, no, it's the same flask. I just shook it around a little bit and it changed.
It looked kind of like magic.
Well, it's not magic. Like you said, we don't do any magic up here. It's science. But if you watch again this time, well, if you actually watch this time, I can do it again. So remember it was that yellow goldy color to begin with. Now we got a amber. Now we got a nice red. And if I really shake it around for a minute, we should get something else. There it is. Green.
They were anticipating that one.
Yeah.
Well, okay, I was watching. You did not switch flasks.
I didn't. It's the same
So
one.
that wasn't magic. What was it?
Science.
All right, so you got to explain what you just did, because
All right.
I don't know about all that.
Well, this is a chemical reaction with oxygen in the air. So just like we need oxygen to breathe, this thing needs oxygen to work. So it starts off as a yellow color, and then when I swirl it around a little bit, it gets a little bit of oxygen mixed in, and it goes to a red. And then if you really shake it around, you mix a whole lot of air, and a lot of bubbles go into it, and that gives it a ton of oxygen, and it goes green. Now, as you see now, it's starting to change back. So what happens once you give it all this oxygen is the chemical reaction is still happening. So it's using up the oxygen that you gave it, and eventually it'll turn back to being red, and then eventually go back to being amber. So it's repeatable. So now it's kind of in between green and red, but if I shake it around again, we'll get back to the green color. So it's actually called the chemical traffic light, because it's got all three colors of a traffic light in it.
Well, that was kind of cool. Dan can make stuff change colors by
Yeah.
shaking around, whatever.
Yeah.
I can do that too with electricity. So, what color do you guys see? Green?
It looks like a light green to me. I think it's kind of a yellow green.
Hey, yellowish green.
That's what I think.
What colors do you see now?
That's red and green. Well, hold on. I agree with the green. I mean, it's clearly green, but I don't see any red. What are you guys talking about?
You gotta pay attention.
Oh. What? Wait a minute. So when you hold that thing still, it's just the one color, like that light green. But then when you move it, it's two colors?
That's right.
That kind of seems like magic.
Is it magic? Well, what is it?
All right. Well, then how do we explain this one? Uh-oh. Time to go.
Okay.
No, stay here. We got more.
All right. So I'm on the hook to explain this. So what this shows us is a concept called persistence of vision. Persistence means it stays. Vision is what you see. So it literally means stays in your vision. What this actually is two LEDs that are flashing back and forth extremely fast. And when it's standing still, the two colors are moving so fast that they stay in your vision, and your eyes can't tell the difference. It just kind of melds together. But whenever it starts moving, the colors, they separate, and you can see both of them. So it's actually not a motion sensor like you guys are seeing. This is a concept of physics, that your eyes literally can't track a moving target like it does a still target. Now what's cool about this, though, is your TVs work the exact same way. So when your TVs at home, they don't put one picture up on the screen all at once, but they put slices of the picture, and they put it up so fast, and it's not moving, that your eyes can't tell the difference. And so you see a constant frame, when in fact, it's putting slices up there so fast, your eyes can't tell the difference. But if you were to take your TV off the wall and shake it all around, the image would fall apart. But the TV might be a little heavy. I wouldn't suggest actually do it.
They're expensive too. Your parents probably wouldn't want you shaking your TVs.
I don't think my one, it'd kill me.
You could try moving your head around really fast.
That's right.
Anyways, all right, so he was able to make light of different colors using electricity, and we can do the same thing with chemistry, actually. And you guys probably know what this is. Have you guys heard of glow sticks before?
Yeah, they've all heard of glow sticks, Dan. Big deal.
Yeah, glow sticks are awesome. The way that those work is it's a plastic tube, that has one chemical in it, and inside of that is a smaller glass tube that is a different chemical. And so when you want to turn the glow stick on, right, you bend it and it makes that crackly noise. That's because you're breaking the glass on the inside tube, and it lets those two chemicals mix together, and then they glow for a while. So that's kind of the idea, is there's two things that we mix together to have an effect happen. So for this experiment, I think I'm going to need Gavin's assistance.
My help?
Yeah.
With chemistry?
Yep. So you need to get ready for chemistry. I gotta get my stuff out, but you go ahead and get ready.
Get ready for chemistry. I'm ready for chemistry. I'm loose and ready.
That's not really what I meant.
Well, what do you mean?
You gotta get your safety gear on.
Well, I've got my lab coat.
Yeah, that's good.
Got my gloves.
Also
So
good.
I'm ready to go, right?
Yeah, hold on. We need one more thing.
What?
Eye protection.
Eye protection.
Something for your eyes.
Eye protection.
So I gotta get my gloves too.
I've got eye protection.
You get those out.
I'm ready.
What are those?
These are the most stylish things on the market.
Jeez. Well, they are very stylish, I'll give you that. And it's almost summer, right? So we'll need them pretty soon.
Yeah.
But not today.
But not today.
Because they're not good. Because, like, let's say I was over here mixing chemicals and stuff, and something went wrong. Stuff could still splash in from the side here, because it's all open. So stuff could splash in and get you in the eye still.
Well,
so, like they were saying, which is very good, we need goggles, real goggles.
Oh, I've got some goggles.
So, these will protect us from all angles, from any possible splashes.
Oh yeah, you're right. There's nothing getting in there.
Eh?
That's good. It's good to go.
You gotta test your goggles before you use them. All right, so yes, so we've got our lab coats, our gloves, and our goggles, and we're all set. So like I said before, there's two things that we need to mix to have an effect to happen. One of them is in here, so kind of a greenish colored liquid, and then there's another one in here that's like a little clear liquid in a beaker. So you can take the beaker,
Okay.
and then what I'll have you do is just take maybe just a little bit of that and just kind of pour it into the cylinder here. And then we should get a nice reaction to happen.
Okay. Where are you going?
Well, it's a better angle from this side. I just wanted to be able to see it better. Yeah,
Okay.
just go ahead, it's fine.
All right.
Yeah.
That didn't look like a glow stick, Dan. Man, I gotta get a knock on my side. What is this? What?
It's a good audience.
That is not. That is definitely not a glow stick.
Yeah, well, that's what he gets for shocking me in the beginning.
Okay.
So, no, you're right. It wasn't a glow stick. Actually, what this was is hydrogen peroxide. So there's a little model of it. So if you had a super powerful microscope and you could look really, really closely at this chemical, that's the shape of the hydrogen peroxide molecule. And what we did here is we added this other chemical to it, and it actually broke it apart and turned it into water and oxygen. And oxygen's a gas, like I was talking about earlier, and it blows a bunch of bubbles and sometimes makes a big mess.
Yeah, a really big mess. Lots of bubbles.
Yeah. And you know, hydrogen peroxide is actually, you can buy that at the pharmacy. You know, it's something for you put it on like a cut and it helps it to heal. But what you can buy normally is only 3% peroxide, which means it's mostly water. What we used here is actually 35% peroxide, so it's more than 10 times stronger than what you can normally buy. So.
Well, you promised them glow sticks, Dan. Do you actually have glow sticks?
I do have glow sticks.
Oh, okay.
But I actually will need your help for that part.
Yeah, right.
Yeah,
I
come
trust
on.
him.
Yeah, totally.
I don't want to see you get it. Well, we're kind of even, right? I mean, I shocked you.
Right.
You pranked me. All right. I guess I'll have to.
Yeah,
trust
we're
you.
even now, so it's gonna be all right.
Even Stevens.
So this time I've got 3 flasks, and I'll give you this red one.
Okay.
And I'll have a clear one here that Here, look, I'll stay here this time. Does that make you feel a little better?
Yeah, a little bit.
All right. So I'm going to add some of my clear solution to his red stuff, and we'll see what happens.
Yeah, that's pretty cool now. Hey, look, I'm Rudolph the Red-Nosed Reindeer. This gives me an idea. Sometimes Dan and I like to take a break from all the science and do a disco break. Got our disco break in for the day. That was good.
So, all right, so it glows, right? So it's a very nice red color. I have a third flask here, so let's try this same one. So this is kind of maybe a yellowy colored liquid. Now let's add that same clear solution to this one. Oh, yeah. Now see,
Dan.
if I swirl it around to mix it all better, then it glows really brightly.
Oh, Dan, I just heard I heard a good idea, a good question. What do you think would happen if we mixed them together?
Interesting.
I think I want to do it.
Interesting. Well, that sounds like a request for science. So, if we're going to do this, though, we got to do it the right way. So we have to follow the scientific method.
Scientific method, I know what that is. Oh, I'm ready.
Yeah? Okay.
I'm ready this time.
Good. Well, the first step of the scientific method is to ask a question. And that's what, that's what you guys did, actually, is we want to know what happens when we mix them. So the second step of the method is to form a hypothesis, which is basically a guess as to what we think will happen. So, what do you guys think would happen if we mixed these two together?
I'm hearing purple, I think. And
I heard some purple.
I agree with him. I think it's going to be purple.
Okay.
I think it's going to be purple.
All right, so we'll go with purple maybe. And now the next step, of course, is to do the experiment and see if we were right. So I think let me see here, this red color is really dark compared to the blue. So let's just add a little bit of red and see what this one does.
That's orange. That's not purple.
That's not purple at all.
That's a completely different color. Well, that means we were wrong. But is that a bad thing?
No, see, that's the cool thing about science and the scientific method. There is no such thing as a failed experiment. So what we just did here is we asked a question, we made a hypothesis, and we ran an experiment, and it turns out our hypothesis was wrong, or at least mine was. I thought it would be purple too, but this is clearly not purple. But what that means is now we can ask more questions. So we can ask more questions like, why did it turn this color? Is there some other way we could mix these to make purple? Maybe are there any other colors we could make? And all of those questions are more science experiments that we can do, and that's just a lot of fun to be able to do more and more science.
Now, Dan, to keep with our tradition of not doing magic up here, you actually have to explain what you just did, other than I mixed a couple chemicals together. That didn't work.
Okay.
So what did you actually do? Kind of explain it.
Okay, well, the reason that these work is they store energy, basically. So it's sort of like a battery, I guess you could think. So when they're separated, they don't do very much on their own, but they have a lot of potential to do something. So when you mix them together, all that energy gets released, and it turns into light. And now, like light bulbs in the ceiling, those obviously make light too, but they get really, really hot. You don't ever want to touch a light bulb, it's super hot. But these things don't. They just produce light and no heat at all. So it's actually pretty cold to touch, which is pretty nifty.
Now, Dan, you said a word that got me thinking. You said energy.
Yes.
And as an electrical engineer, I like electricity. And electricity is a form of energy. Now, you were also talking about light, so I think I'm going to go down that track to try to show you up. Whenever you go home and you want to start reading, what do you need if it's dark in the room? What do you need? You need a light. You need a lamp or a flashlight. We've got huge spotlights over here to light us up. You've got lights in the ceilings, and sometimes you've got simple lights like this. Just a fluorescent bulb. This is just like what's in some of your ceilings. probably
Yeah,
in your classroom.
Yeah, I see the cord going to the wall, I guess.
Yeah.
Eventually.
So that's all good and well when it's plugged in.
Mm-hmm.
I'm going to light this light bulb up without any wires.
Wait a minute. Hold on. So you're telling me that this is just a light bulb? It's just a light bulb, right?
Just a light bulb.
So there's no wires connecting it to anything?
Nothing. No, nothing
Okay.
there.
There's no batteries on it?
Nope.
All right. And you're saying you're going to hold it in your hand and light it up?
That is correct.
You'd have to use magic to do that, wouldn't he? What would he have to do? Science?
They're a little weaker on that. I think they think it's
they're not
magic.
sure. They think it might be magic.
All right. For this part, I'm going to need your help, Dan, if you don't mind.
See what I can do.
So, what I'm actually going to use to light this up is the power of lightning. What comes after lightning? Thunder. So this next part might be a little loud. If you're worried about that, you can cover your ears. But I am going to use the power of lightning, believe it or not.
Y'all set?
Yep.
Okay. I'm not sure I'm qualified to operate this.
Oh, I'm sure you'll be all right. Hopefully.
Okay. Here we go. Look at that. It's lighting up. It's like a lightsaber. Like Star Wars. Wow. Wow. Hey, yeah. Nice.
The lightsaber, you're right.
Oh, I gotta turn it off.
Yeah, let's turn that off. Finally, some support. I appreciate that. Thank you. About time.
They seem to like that one.
Yeah, I'm telling you.
Dang, well, that was, I gotta admit, that was pretty awesome. But I don't understand what happened. I mean, you had this lightning contraption back here, and then you were just holding on to this light bulb, and you were still, I don't know, 3 or 4 feet away from it, and the light bulb was lighting up.
That's right.
That's gotta be magic.
Is it? Then what was it? You're picking up on it.
All right, good. Well, how does that work then?
All righty. So in order to explain this, you're going to have to work on a history lesson with me. So who here knows about Thomas Edison? Yeah, a couple of you. What is he famous for? The light bulb, that's right. How many of you have learned about Nikola Tesla, though? Oh, a couple of you.
Oh, cool, a couple people.
So Edison may have invented the light bulb. Tesla invented or discovered the power that we use to power up Edison's light bulbs. So the big transformers and the substations and the power lines you see running on the long side of the road to your houses, those are all inventions of Tesla. Now, Tesla learned how to create and transmit power with cables, but I tell you what, who here hates tripping over extension cords?
Yeah. Oh yeah, there's tons. We have tons of. You probably tripped over a bunch of them coming in here. We have tons of them all over.
They're all over the place. You got to be careful. Well, Tesla hated that too. So he decided he wanted to figure out a way to transmit power wirelessly or without any cables. So he invented the Tesla coil. And what this coil does is it literally soups up the power that comes out of the wall so high that it becomes lightning, like you guys saw. And you're able to transmit that power. You saw it go into the dome, and you saw it going into my light, lighting up the light bulb. Now, some people have talked about using this in everyday life, and if it was actually practical, we could power everything. We could power our cell phones, we could power our TVs, our computers. Some people have even talked about powering neighborhoods with it.
Yeah, but, so you wouldn't need any batteries for anything, right?
That's right, no batteries.
Would just work.
Yeah.
That would be real nice.
But the only problem with that is, did you guys hear how loud that was? That was pretty loud, wasn't it?
Yeah.
And in order for it to power a neighborhood, it would literally have to shoot, it would have to be 100 foot tall, first of all, and shoot 100-foot lightning bolts all day long, which would be cool for about 5 seconds, and then you get tired of it, because it's so loud and obnoxious.
Yeah, and it doesn't sound very safe either, lightning blasting around everywhere.
Yeah, I don't think the birds would appreciate it.
Maybe not. You've eaten chicken a lot more. All right, well, I do have to admit that was very cool. Let's see if I could do something similar. Okay, so like he said, that made a lot of noise. It's very loud. We can do something with sound, with chemistry as well. First, I want to talk about gases, though.
Oh, Dan, don't talk about gas. That's disgusting.
No,
Oh,
not that kind of gas. No. Like I'm sure you guys have learned about the 3 states of matter, right? 3 states of matter. We got solids, we got liquids, and then gas. Like air is a gas.
oh, okay. False alarm. Sorry. I thought he was talking about another type of gas. Yeah, you know what I'm talking about.
So yeah, air is a gas. Besides air, there's lots of other types of gases, and one of them you probably know about. Those party balloons that you get for birthday parties. You know what's inside those? Helium. Helium is a gas that is 6 times lighter than air. So what happens if you have a helium balloon and you let go of it? What does it do? It just flies away from you. And it's very sad. But it does that because it's so buoyant, right? So it's sort of like if you had a beach ball and a swimming pool and you try to push the beach ball under the water. It's really hard because it really wants to float. That's kind of what helium wants to do in air. It'll just keep floating until it reaches outer space. So helium is 6 times lighter than air. Another property that it has that you probably have heard of, but don't try this at home because it can be dangerous. But if you breathe helium, do you know what that does?
Oh yeah, it makes your voice really squeaky like this. Like that?
Yeah, something like that.
That's what I thought.
So but don't try that because when you're breathing that gas, you're not breathing air. You're not getting the oxygen you need, so it's a little bit dangerous unless you are a professional like we are. So, helium is very light, makes your voice squeaky. I have other gas down here that you probably haven't heard of before. Before I talk about that, though, I have one final job for you.
Another job?
It's it's easy, though, I promise.
Okay.
All you got to do is blow up a balloon.
Oh. Well,
Yeah.
I guess I could do that.
So that should be, that's not too hard, right?
Here's hoping.
So he's going to blow up his balloon with air, right? So of course the air inside of that balloon is going to weigh the same as the air.
Dan, I lost my balloon.
And that's all dirty. You don't want that.
Yeah.
I got enough
Do you
here.
have another balloon, maybe?
All right. You the same color. How about that?
Okay. I'll try not to lose this one.
All right. So his balloon is, like I said, is going to be filled with air, hopefully, and it's going to weigh the same as the air outside of it, right? Because the air inside is the same as the air outside. So if he lets it go, it'll just kind of drift down slowly. My balloon, I filled up earlier using this gas that's in these gas cylinders here. Well, if it was helium, if I let go of this, what would happen? Doesn't go anywhere. So probably not helium. What it actually is sulfur hexafluoride.
Sulfur hexa what?
Sulfur hexafluoride.
I think he's making up words. What do you guys think?
No, it's a real. If you can spell it, you can look it up. It's a real thing. This is a model of it again. So if you had a super powerful microscope and you could look at this gas, this is the shape of the sulfur hexafluoride molecule. It's very big. Helium is about the size of one of these white ones, whereas SF6 is huge by comparison. So that means that this gas is actually very heavy. It's actually 6 times heavier than air. So it's sort of like the opposite of helium. So what I think we should do with our balloons here is have a little balloon race.
A balloon race?
Yeah.
How do we race balloons, Dan?
Well, you have to. I think there's an official rule book. Yeah, you just chuck them at the audience. No, you don't do that.
Well, that didn't work.
There's like a rule book, I think, and you have to like take special courses to be qualified in balloon racing, and you have to have a judge. And
Do we know anybody like that?
I don't know if anybody's actually taken the courses.
Yeah.
Guys, of course you do.
Do you know how?
Yes. I'm an engineer. We do this type of thing all the time.
Okay.
Well, guys, this is our sister Kinsey.
Hi, guys.
So you know how to race balloons?
Yeah, I know all about physics, and it's real easy.
Okay.
So what you gotta do is you gotta drop it from the same height at the same time and see which one hits the ground first.
Sounds easy.
Yeah. All
Sounds
right.
simple enough?
I'm on it.
All right, so we'll start right about here. No, you're so close. Oh, okay. Brothers.
Okay.
We'll get there one
How about
day.
that?
All right, okay. All right, you guys can count with me? Yeah. Okay, so we'll do 3, 2, 1, drop. Ready?
All right,
I'm ready.
Ready? 3, 2, 1, drop.
That was like magic. What was that magic, Dan?
No. What was it? Yeah.
Okay, well, we'll do it again just in case.
Okay.
Now, science is all about repeatability.
That's right, yeah.
So,
That one.
yeah, if I can say it, we can do it. All right, so we'll do it higher this time.
Okay.
Not that high, I'm pretty short.
I'm on it. Right here. All right.
Okay. All right, ready? 3, 2, 1, drop. Wow, you did it.
Sweet.
One by a
2 in a row.
landslide. Okay, Dan, explain yourself.
All right, well, it may have been science. Like we said earlier, this gas, sulfur X fluoride, is 6 times heavier than air. So even if our balloons were exactly the same size, mine would weigh 6 times more. So it falls a lot faster because it's heavier, which is pretty weird. It's actually weird to hold. It almost kind of feels like a water balloon when you're holding it, but there's no water in there. So like I said earlier, it's like the opposite of helium. Remember, helium is 6 times lighter. This is 6 times
Okay, Dan,
heavier.
Dan, I have an idea.
Okay.
So, well, I have a question, really. So if this is like the opposite of helium, and helium makes your voice really, really high, then what would this do if you breathed that gas?
Interesting.
I hear a request for science.
All right, so let's do the scientific method again. The question was, what would happen if I were to breathe this? What is your hypothesis? What do you guys think?
I think your voice is going to get deeper, Dan.
Okay.
Yeah.
So let's actually do the experiment now and see if we were right. And I did research this, so it is safe to breathe. Don't worry. So I'm just gonna breathe out and breathe it in, and we'll see how it affects my voice.
Now my voice is a little bit deeper. I think it's slightly lower. Is it, what, is it a little bit? It's a little bit lower. So yeah, I think you guys were right.
Why don't you sing him a song, Dan? That'd
Okay.
be a good one.
Old Man River, that old man river.
Yeah, that kind of reminds me of what you did for Halloween last year.
Oh yeah, I was a mad scientist for Halloween. Well, tiny bit left.
I don't know if I trust it, Dan.
There's a little bit. It's not a ton. But it lasts a really long time. You see how long it's still. I'm still talking, so I got to get it out of my lungs.
So guys, what do you think? Yeah, this is kind of weird. I don't know how I feel about this.
As long as your normal voice comes back.
Yeah, so we have to, it's so heavy that it stays at the bottom of your lungs. So we have to force it out of our lungs. Like helium is so light, it just flies out of you. This gas is so heavy, we have to force it out by breathing really hard.
Am I back to normal?
Yeah.
I
Okay.
think so.
All right, I'll keep it this way.
Well,
All right.
that's all cool, but I lost a race.
Oh.
Do you have anything that maybe I could have a scientific advantage in? Because I feel like he kind of cheated.
You know,
Cheated.
I just might.
Really?
Yeah, but I need a couple things
Okay.
first. I'm gonna need a cup.
Cup.
Like plastic cup, green, red, blue, whatever.
Here we go, I got one.
Cup.
Oh.
Cup.
All right,
Okay.
and then I'm going to need something to put the cup on. Right about
Well,
that's all.
that's a little bit taller than the tables.
Yeah, no,
It's
that's
too tall for us.
way too short.
Yeah. That's
You're about that tall?
that's about the height of one of those people out there, isn't it?
Ah.
I don't know though. They have to be like a really, really still, really, really quiet student.
Ah, so this is like tryouts. So if you guys want to volunteer, raise your hand. We're trying to be still and quiet.
Still and quiet.
Ah.
All right, you right here. What's your name? Craig. All right. Okay, Craig, you can stay right here for me. All right. So what's gonna happen is I'm going to place this cup on the top of your head. You think you can handle that? All right. Let's try it. Ready? Perfect.
Ah, good.
All right.
He's
Can
good.
you hold that for me, Craig? All right, Dan, your turn first.
Okay,
You're gonna
what am I
step
doing?
right up here for me.
All right.
And when I place the cup on top of Craig's head, you're gonna try to knock it off. Think you can handle that?
Okay.
All right. Ready, Craig?
I'm ready.
All right. Drum roll, please. Go. Not even close. Here you go. You can take a little break for me.
He's too far away from me. That's impossible.
Is he? Is he? All right, Gavin, it's your turn.
I'll go to the same
Step
spot.
right
Good
up.
luck.
Now, before you go, let me grab my scientific advantage.
What is this thing?
Yeah. All right. So once again, cup's gonna go on top of your head. Say super still for me. Okay.
Oh, okay. To the other side. That's good.
All right. You ready?
I think so.
Ready, Craig? Ready? Drum roll, please.
Oh, I saw it move a little. Oh,
Did that count?
I don't know. Did it go?
I don't know.
You knocked it off. Let's
Did
try it again.
Did I knock
Ready?
it off?
Just slip the other way.
oh, it's like jumping around. Oh, nice.
Did you feel anything? What'd you feel? Bunch of air.
Air,
All right,
yeah.
thank you, Craig. You can have a seat.
Thanks.
Good, Craig.
Yeah, I didn't see anything. But
There's something coming out of it.
Well, no, and you won't see it because it's air.
Okay.
And you know, I could explain it, but honestly, I'd like to show it. Dan, Gas Master, do you have something that can make air visible?
I might just have the gas.
Awesome, because I have a vortex cannon.
Whoa, that's big.
This is basically a bigger version of what I gave Gavin. So what this is, we'll fill it up with.
All right.
What is this here?
It's this little smoke machine like you get for Halloween times. So I'm just gonna make a bunch of fog, and hopefully you'll be able to see air with that.
All right, so like I said, this is a bigger version, and what it has is the circle cut out in the middle. So what I'm going to do is I'm going to force air out through it really fast, and it's faster than the air around it. So what it does, it creates a vortex.
Wow.
Look how far they're going, too.
Yeah, and they're
That's crazy.
really stable.
Yeah, look how long they last.
It'll just keep going for really far.
They do just keep going. Try going back this way so it stays in the light. I guess not.
Ah, too long.
Yeah, you can make like negative rings going through.
Rapid fire.
Wow.
Man, that's pretty cool.
That, what
Yeah.
you're seeing right there, is actually what knocked the cup off of Craig's head. It was a blast of air.
Okay, so that
I'll
ring is
explain.
what did it.
Ah,
Yeah, it's the ring. It's the vortex.
well,
That's
very
pretty
nice.
cool.
Yeah. Well, thank you, Kinsey. That was awesome. Give her a big round of
thank you.
applause.
That was very cool.
Bye, guys.
Man.
That was pretty cool.
Yeah, that was cool. They were really stable too. You see how long they lasted? You just kind of kept going. Oh, all right. Well, we've talked about a lot of different things today. A lot of different concepts in science, like light and sound and color and energy and motion and things like that. And I want to bring all of that together into my favorite demo that's called Barking Dog.
Barking dog. Dan, you can't have a dog in here. Where's your dog?
Well, this is the dog right here.
That's your dog.
Yeah.
That must look pretty funny when he's trying to walk the dog.
Yeah, he's not very cooperative. I have to drag him around. No, it's a glass tube is what it is, and it's filled with two gases that we haven't talked about yet, and both of them are invisible, so you can't see them. They're in there. One of them is called nitrous oxide, which is also known as laughing gas.
I laugh when Dan has gas too.
Enough with the gas jokes.
Never.
So laughing gas, they give it to you at the dentist's office sometimes. They put like a big Mickey Mouse nose on you, and you breathe the gas, and it makes you fall asleep. Anyways, that gas is in here, and then there's another one called methanol, and both of these gases are swirling around together, mixing, and they don't do a whole lot on their own. So what we need to do is give them a little bit of a kickstart before we can get a reaction to happen, and we're going to provide that with a lighter.
Huh.
Well, but
Before we use the
remember,
light,
yeah,
What do we need?
safety first. So we got to get our goggles back on. We're getting these big heavy gloves now. And we've also got a big safety shield as well. So, don't do any of this at home, right? Don't play with these at home. What we're going to do here, this reaction, Gavin's going to take the cap off of the tube here, and I'm going to ignite the gas mixture with the lighter. And it's going to happen very, very fast, so don't blink or you might miss it. And it's going to be pretty loud, too. So just cover your ears if you want to.
All right. You ready?
I think so. Okay, here we go. That's the bark.
That was cool. That was pretty good. That's pretty good, Dan.
That only works once, unfortunately.
Well, we're pretty much to the end of almost to the end of our show. But whenever we're not done yet. But whenever I go home personally after a long day of science and all that, I like to relax with music. Who here likes to listen to music?
Yeah, I like music.
That's what I figured. That's what I figured. Now, you guys probably listen to music with speakers and headphones.
Well, yeah, of
and all that
course.
kind of stuff. Well, I like to listen to music using my Tesla radio. You guys want to hear my Tesla radio? No? Or you don't have to.
No, we'll just pack up.
All right, I heard a yes. Okay.
I'm gonna go over here, I think.
Let's see if we can't make this thing to work.
That's slow. It's this thing again.
Sometime today. Alrighty. Let's see if we can't make this work for you all.
Always a lot of setup with electricity. They recognize that. Star Wars movie.
You might know this one. Yeah, there we go.
Nice. Nice. That's pretty cool. I have to admit that was really cool. I do have one question though. Was that magic?
And what was it? Pick it
Well,
up.
then how does this thing work? Because I didn't see any speakers, so I don't know where's the sound coming
Didn't see any
from.
speakers. So, just like I used the power of lightning earlier to light up my light bulb, what did we say came after lightning? Thunder, that's right.
Thunder, oh.
So, using my laptop over there, I was able to manipulate the lightning, and what you were hearing was the different frequencies of the thunder that came after the lightning that came out of my coil here.
Dang. So you were controlling lightning over there.
That is exactly what I was doing.
That's real mad scientist stuff right there.
pretty cool. All things said, I've got a confession to make. This hurts to say, but I think Dan showed some pretty cool chemistry stuff. That was pretty cool, Dan. What do you guys think? It was pretty cool. Yeah.
All right, thanks. And I gotta say too, he had some pretty awesome stuff too with electricity. You guys like electricity?
Aha. We got him even again. That works.
Yeah.
Oh.
All right.
Well,
That's
I
think that's about our show then. So
Yeah.
thanks a lot for coming, everybody. I hope you guys liked it. Hey, anybody want to be a scientist now? You want to be a scientist?
Anybody? Yeah, a couple.
All right. If we have a few minutes, teachers, we could answer questions possibly.
Do we have a few minutes?
Time?
I can't see if they're saying yes
Okay.
or no. So.
I heard a couple of yeses. That's the
Okay.
answer I'm going to go with.
Okay. All right, go for it.
All right, how about you in the front here with the purple?
I'm wondering how you make the bottle flow.
Oh yeah, the glow. She wants to know how the glow sticks work. It's not as interesting as some of the other ones, to be honest. I bought them. I bought these from the same company that makes regular glow sticks. You can buy big barrels of the same chemicals. Actually, ours is super concentrated, so I don't know if you noticed, but this is really super bright. The ones that are in normal glow sticks, they glow for a long time, but they're kind of dim. This stuff glows really, really brightly, but it doesn't last very long, which is perfect for us. But yeah, I bought them. They're two very complex organic type chemicals, diphenyl oxalates, and I forget what the other one is.
Gesundheit.
I'd have to look it up, but yeah, I basically bought them, and you mix the two and they glow.
So it's the exact same thing as normal glow sticks. The same mixture.
Pretty much.
essentially.
Yeah, same mixture, just a bit more concentrated.
Okay. Alrighty, my turn. I get to pick one. Let's see. Alright, you in the blue right here. Yep.
How do you make it work?
How do I make what work? The Tesla coil. Okay. All right. So we get power from the wall, just like everything else you plug into the wall. But using my Tesla coil, all this red is a bunch of wire. It's coiled up and it's wound up really tight. So it works like a transformer. So you give it a little bit of power in, and it amplifies it and gives you a lot of power out. So much power, in fact, that instead of having to have a cable like we were talking about, we want to do it wirelessly. This literally uses air as its cable because the power is so high, the lightning ionizes the air and it wants to travel to this dome, which is ground, which is just like every other electrical circuit, except this time we're using lightning and air instead of normal electricity and cables.
Yeah, that's a ton of power to be able to shoot
Yes.
through air like that.
Very
It's a very
dangerous,
good
too.
insulator. All right, how about you in the blue, second row? Oh, the traffic light. How do I make the traffic light change colors? Well, like I explained, it's a reaction with air. So see, now it's back to being yellow because I left it alone for a while. It's a reaction with air, right? So you mix a little bit of air into it, and it goes green, and then you mix a whole bunch of air into it, it went red, and then you mix a whole bunch of air, and it goes green. This is actually, what's in here is water to dissolve everything. There's sodium hydroxide, which is also known as lye, and there's dextrose, which is a type of sugar. So it's basically lye and sugar, and then there's a dye also called indigo carmine, and the dye is what is changing the colors. The other things are there to just kind of help the reaction along.
Alrighty, third row, white shirt. Yep. Okay.
Hey, all right. Where can I find work as a chemist? Oh, there's tons of people that need chemists. You know, chemical engineering is one of the highest paying jobs there is.
That's true.
Chemical engineering is hard, don't get me wrong. It's not an easy job, and you need to go to school for a very long time. But it's very, very rewarding. I mean, there's so many things that require chemistry. I mean, you think of, oh God, what's a good example? Sulfuric acid, I think, yes. Sulfuric acid is a chemical that's produced so much that they judge how well developed a nation is by the amount of sulfuric acid they produce. Wow. So you need a lot of chemical engineers to be able to produce that acid very efficiently. And like another good example would be fertilizers. So farmers, everybody that grows crops and stuff like that, they need a lot of fertilizer. And you make fertilizers using chemistry. You get nitrogen out of the air and turn it into nitrates, and that goes into the soil and feeds the plants. So, yeah. So there's lots and lots of jobs for chemists out there, definitely. Okay, how about way in the back, right on the blue stripe there? Yeah. Yeah, the barking dog. That one is green actually because of boron. So there's a thing in chemistry called a flame test. If you have a substance that you don't know what it is, if you put it into a flame, it'll change colors based on the metals that are dissolved, that are part of the compound. So like if you use table salt, it's sodium chloride, you put that into a flame and it makes a bright yellow. If you do lithium chloride, it'll be bright red. This was boron, boric acid actually, but it has boron atoms in there. And the boron, when it burns in the fire, imparts a green color to it. So there's other versions of this actually that use sulfur, and that makes a blue color. The sulfur version is a little bit nasty though, so we don't like doing that one.
Okay, so we're at the 2-minute mark. We get 4 more questions.
4 more questions. All right. Go for it.
All right, tracksuit right here.
I want to know what that weird thing does with all the bubbles.
With all the bubbles.
Yeah, it's a decoration really. It's just it's got an air pump in the bottom and a light bulb. So it's just like, you know, it's like what you have in your fish tanks.
He just wanted to look fancy.
Yeah, he's got his little glowing square down there, and I wanted something else that was moving.
They don't do anything.
Okay, 3 more.
Cool.
Go ahead.
What about you right here, white polo?
It adds to the ambiance.
When you touch the lightning,
Touch the lightning.
not good things.
No, so the easy answer is you would get plasma burns because that's what you're seeing coming as lightning. But if you were to touch it and you were a good path to ground, that lightning would travel all the way through your body, and in some cases it could even stop your heart. It's very, very dangerous.
Yeah.
And you have to, that's why I have to stay a good distance away from it while I'm operating it, because if I touch it, not good. Not good.
We don't suggest it.
It is
All right.
lightning after all.
How about way in the back, blue shirt? I'm sorry?
The orange.
Yeah. Oh, can we? It would just make it really red right
Yeah,
now.
yeah, it just turns. The red is such an overpowering color. We have green versions of this too, but even that, the red just washes it out completely. So it all just ends up looking red.
Okay.
So, one more?
All right, last question, right here. The bubble?
Oh, yeah. It's called Elephant Toothpaste. Is the name of that demo. So you can look that up online if you want to. It's hydrogen peroxide, and like we said earlier, hydrogen peroxide, when it decomposes, it turns into oxygen and water. And oxygen is a gas, so that takes up a lot more room than a liquid, and that just makes a ton of bubbles. And we use 35% peroxide because that's got a lot of peroxide, so it's got a lot of potential to make oxygen. What you can normally buy is 3%. You can do this with 3% peroxide. It's just not quite as impressive, but you could certainly try it. Go home and there's a safe version of the Elephant Toothpaste that uses regular 3% peroxide and yeast, if you have any of that. So you could give that a try when you go home. But you can get, there's up to 90% peroxide, which is horrifyingly dangerous when you get to that concentration. But that would they actually use 90% peroxide as rocket fuel. So you can imagine that makes a lot of gas in order to propel a rocket.
Good, great. All right.
All right.
All right, well, yeah, thanks everybody. I hope you guys liked it.